nice room in this beautiful setting. You can watch the snow speaking, so that's really amazing. So today I'm going to talk about optical neural networks and diffractive types. So this means we have an optical image, an optical field, comes into a physical system, it gets diffracted somehow. And the light is focused onto some specific areas to perform some classification tasks. So this work was done by my student Romani, together with my postdoc Guillaume Notinger, and also Tim Tuva, who is another student of mine. So before I start, I will tell you a bit about where I come from. So I work on classical systems, I work on waves, wave phenomena, and my background is mainly scattering. So we do a lot of things from very applied things. So what you're seeing here is an antenna that is used for internet over satellite, so just like Starlink, but it has much higher efficiency, which allows us to speak to GEO satellites, so we don't have to send to crowd space with new low orbit constellations. And we have a startup on this. So this is like really applied part of my research, and then we have some more fundamental things about disorder and scattering and disordered system. And this talk is going to be about this part. So I'm not only focused on neuromorphic computing, it's part of what I do, and we are trying to use wave scattering to do computing. We also do, for example, acoustic tweezers in complex media and things like this. So perhaps half of my talk will be some very general things about optical computing, wave-based networks. So I'll give you some basics and then we'll move on. So back in 2018, and as Peter explained, the CEO of Microsoft was quoted to say this famous sentence: "The world is rapidly running out of computing capacity." And this was already in 2018. And why is that? Well, because on one hand, we have Moore's law. This is the saturation of the number of electronic components we can put in a microprocessor, and this saturates. But the need is skyrocketing. We can calculate that the need is of computing power in the world is we need an increase of 300,000 times over 5 years, and Moore's law can provide only 7, a factor of 7. So there is a lack of computing power. And why? Well, of course, this is because of AI. And AI systems, they work with a lot of parameters, you have to train them. They are now increasingly complex. And this increases a lot the number of parameters you have and the size of those models. This is problematic because it uses a huge energy, and the energy consumption is just skyrocketing as well, not only for training but also for inference. And inference is something that happens continuously. It's not like training, you do it once. Inference, you do it every year. That's why this energy is a cost per year. So this is of course a major concern. Okay. You've probably seen this in the press. For example, the fact that the good old Google search bar was consuming much less than the same prompt on ChatGPT, and for example, this is this prediction that the energy cost of AI will be in 2030 as much as twice the energy consumption as France. I think this should be a concern for everybody. So that justifies us to do research in this field. Okay, so some questions that I'm asking myself. I'm not saying that I will answer all of them, but these are questions we should have in mind when we do this type of research. So can analog wave system perform similar tasks? So analog by opposition to digital. Analog systems are systems where information is encoded continuously into physical variables, not into zeros and ones in transistors. But more importantly, can these systems help compute with less power, or at least with some advantage? When we compare them with digital systems, And what are the challenges and opportunities in developing wave systems for AI? So myself, I'm a specialist of waves, so that's why I focus a bit on waves. And I will narrow down this talk to optics. Okay. So this talk is really about using waves to do AI. So I mentioned this nice paper by Oscan, and it was a microwave experiment. They have a field where there is an image, for example, it encode 5, and then this electromagnetic field is scattered by a few layers. There are 3D printed plastic layers, it's very simple. And after this complex, and they are not homogeneous, they are very complex, they are designed so that, for example, if I have a 5, it focuses the energy onto one of the detectors and classifies this information. This is another microwave experiment that we have done in my lab a couple of years back, where it's essentially a cavity, okay, like this room, and we have a Wi-Fi network, so there is an antenna, and there is your phone that is able to receive the Wi-Fi network. And on one of the walls, we have what we call a programmable metasurface. It's something that has pixels. It can reflect the electromagnetic waves in phase or out of phase, just 2 bits. And we can encode input data here and classify based on what we receive at one of the receive antenna.
You can put it on your sweater. And there is a little thing to turn it on at the back.
Is it on? Oh yeah,
It goes on here.
on the side. Thank you. So it's not about, it's really about using waves for AI, not using AI to simulate waves, which a lot of people are doing right now. Just and I like this picture to justify that analog computing is something interesting. Although we have forgotten about this for decades. Analog computing is decades late compared to digital computing. If you just look at our brain and the optical nerve and our retina, and you look at what amount of information is coming at us in the electromagnetic field, it's huge. It's 9 megabits per second. And then the optical system of your eye and the retina turns this into 100 bits per second in your optical nerve. And this is processed by your brain, which functions with a few tenths of watts. So it's an extremely efficient system that performs really smart analog data compression and is capable of extracting the information that you need. And you can, this is just amazing. So we should be able to do better with analog computing. So what are the opportunities and the constraints? So as Peter said, it's nice that you can work directly on an input signal in its native form. I receive light and I process light, and light comes out processed. There is no, that's really cool about analog wave processing. It could also be sound. We could imagine a really nice room where if I speak English, the sound gets focused to that corner. If I speak French, it gets focused to another corner. Of course, it would be very fancy, right? But maybe it could be useful in museums. Who knows? I also think that, for now at least, we cannot replace or eliminate digital electronics. Because when you try to actually build a system, you will need to sense the output. What's the result of this processing? You will need to store it. You need to perhaps use digital to handle things like SNR. And therefore, we should work together or complement digital systems to provide either a power advantage or a computational advantage of some sort. So physical neural networks, what are they? They are physical systems with controllable weights that learn complex functions. Something like the output is a function of inputs and weights. And you train the weights so that you can perform a given task. So we all know, for example, perceptron neural networks. Physical neural networks, they look like this. So you have, in my opinion, two sorts of them. You have some that are neuromorphic. They're trying to mimic what happens in digital. Here you have a bunch of connected neurons with a lot of connections. Here you have a bunch of waveguides with a lot of interactions. And you have nonlinear layers. Here you have also nonlinear activation functions. So you're trying to mimic what happens in digital. That's the first type. And the second type would be non-neuromorphic physical neural network. You just take any system, it's not trying to mimic any topology from digital. For example, this work from colleagues at EPFL, they just use a nonlinear optical fiber, and they have weights somewhere, they have a detector, and they train this to perform some classification. So when I open a physical neural network paper, what questions do I ask myself to sort of understand what's going on? So this is not exhaustive, this is the things that I personally look for. Which physical weights are used for what? So where is the input data encoded? Where are trainable parameters? How many of those weights there are? Is this system scalable? Can we imagine going to tens of billions of weights or not? And why? Okay, for example, I have a screen. This screen is putting an image. This would be encoding only input data. Or there are some other papers that put weights into that screen as well, and everything gets mixed in the system. Second thing is that neural networks, to perform advanced tasks, they need to be nonlinear. So we need to ask ourselves, do we have a nonlinearity in the system, and where? So sometimes it's just a material nonlinearity. If I, for example, in the case of photonics, if I operate at high power, I will have nonlinearity kick in. It's not very good because you want to operate at low power. Sometimes the nonlinearity is only in the readout. So you have a sensor, for example, a CCD camera. It takes the amplitude square of the field. This square is nonlinear. And that's the only source of nonlinearity in the system. Sometimes there is a digital part where the nonlinearity is hidden. Or we can also use structural nonlinearity, and I will explain this a little bit better in the next slide. Then you can ask about how is the training done? Does it use digital weights as well? How is the loss function evaluated? In most works, it's always evaluated digitally. It's very hard to evaluate loss functions analogically. So there is always part of the system that is digital. You need to, if you want to use a gradient-based training method, you need a differentiable model. Sometimes you use a digital twin, you can use physics itself. You have different techniques, so this is for gradient-based. There's also gradient-free techniques, etc. Other tricks. And then you can look at what task it does. Is it difficult or not? And is it universal? Okay, so I think somebody here should explain about structural nonlinearity, and since I'm going to use it a little bit at the end of this talk, let's get to it. So what it is? Structural nonlinearity. You have a wave system such as this optical Mach-Center interferometer array. So what it is two waveguides for light. They interact with each other, so you can couple light from one to the other, and you have two parameters that you can control, which are phase shifts in the arms. So the two angles identify. And this is a 2x2 scattering system described by a unitary scattering matrix that we know. And you can make from this a more complex system. Let's put three of them together, just for the sake of this example. And now you can decide, okay, let's use this to make a physical neural network. And I have a choice. Where do I put my input? Where do I put my output? What is it? So for example, I propose these two choices. In this case, we say, okay, the input data, x, will be the light, in the light that I send in. And all these parameters will be my physical weights to train. And this will be my output. And since light propagation is linear in these things at low power, you only get a linear relationship between x and y. The other thing you could do is say, no, I don't want to do that. I will encode my input into some of those weights, and my output will be y. And then if you do that, you realize that the relation between x and y is strongly nonlinear, despite the fact that you are using optics at low power. So there is a source here that operates at low power. So whatever the parameters, here you always have linear relation between x and y. But on the other case, if you do this structural nonlinearity, the relation between x and y is heavily nonlinear. Okay, so this has been implemented in different works. This was our work. There's work from Stephen Chico and Quicao, work from Clara, Ranchura, and Florian, and some people at EPFL, Demetri Psaltis, and Chris Moser, and others. They are just examples. So typically, for example, this schematic is this. You send some light into the system, and here you have on the walls some sort of programmable meta surface, and that's where you put your input data. And then the relationship between the input and the output light is, the relationship between this input data and the output light is heavily nonlinear. Okay. So why optics? So there is a really nice paper by Peter Mahon on this. I'm just going to pick up two arguments. The first one is that the optical bandwidth is huge, even compared to electronics. It's 5 orders of magnitude larger. So you have a lot of space in the bandwidth. And this is already used in technology. For example, so you can send different data at different frequencies, different wavelengths. This is called frequency multiplexing, wavelength division multiplexing. And this is used in telecom. You can have 10 to the 7 different frequencies in a frequency comb. So there is a lot of space to encode a lot of weights along the frequency axis. And there is also a lot of spatial degrees of freedom. So this is a calculation from your paper. If you just take a 5 centimeter cubic cavity, how many optical modes do you have? You have about 10 to the 15 independent modes. You take a wafer of the same size, you calculate the number of transistors you can put there, it's of the same order of magnitude, even a bit lower in this case. So it means that you have a lot of spatial degrees of freedom that allows you to parallelize the computation. And this is a measurement that we've done in my lab because we are trying to use that to process input data as a batch. So this channel is independent from that channel, which is independent from that channel. We send here the MDISC data set as a batch on an SLM. So let's explain now what SLM is. A good thing with optics for us researchers is, our job is to show what's possible. We want to show that it's possible to train optical systems. And there's already some devices with controllable weights that have a lot of them, 2 million, for example, for SLMs, and that have been developed over the years for adaptative optics. And adaptative optics, it was initially because when you take the image of a star on a telescope, you have the fluctuation of the atmosphere that blur your image, and you need to sort of create an adaptative optical system with a deformable mirror to fix the wavefronts and clear your image and see the star properly. And this has been developed over the years with systems, with devices called spatial light modulators, which are basically arrays of small elements, either liquid crystal or micromirrors, that can control either in phase or amplitude or both the transmission or the reflection of light. And it means that you can use one source of light, and if you project this to the SLM, here you have 2 megapixels, you have millions of secondary sources that you can control with just one source. And that's really interesting. Perhaps the problem right now is that they are not that fast. At least the SLMs, they're operating in the hundreds of hertz. The ones we have in the lab, they are at 60 hertz. And digital micro mirror device like this, they can operate faster, but they have only 2 states. Typical size is 2 megapixels. So in optics, they have been used beyond clearing the image coming from the stars in a field called waveform shaping. So this is, for example, a layer of strongly scattering sample. That this could be a piece of sugar or a cup of milk. You have light being scattered away. You shine with a laser, and the light that you see at the output is a coherent speckle. So this means a mess, a coherent mess of modes. And you cannot really control it unless you use an SLM, a spatial light modulator, to turn this cup of milk into a lens, for example. It's really cool. And this is done by optimizing all the weights, all the phases that the SLM provides until you manage to focus the speckle at the location that you want. So you start with this randomness, and then little by little you optimize all the weights. So this is already something like a physical network, not exactly, but it performs an operation, desired operation, by tuning weights. So SLMs are great, but they are not going to be GPUs, at least not right now. If you calculate the number of floating point operation they can perform, you have 5 orders of magnitudes to bridge. So compared to a normal GPU. And bridging these 5 orders of magnitudes, you can do it different ways. You can say, okay, I need bigger SLMs, I need to stack a lot of them. 300 bigger SLMs, this is crazy. Or you need to operate them in the megahertz. But there's some groups working on this. All right, the last thing I want to mention, I'm going a bit slow, sorry about that, is the fact that SNR will matter at some point. It's already known in optics. When we measure the transmission matrix through a disordered sample, T, we have methods to measure that, just like the cup of milk that I was mentioning. It relates the output on the camera to the SLM, the field at the SLM. That's called the transmission matrix. And if you want to find a given input to yield an output that you want, you need to invert this matrix. You need to invert a matrix that you experimentally measure that has noise, etc. You need to do some tricks to do that. It's called Tikhonov regularization. And it works, but it doesn't work super well. So for example, these are measurements in my lab. We measured a T matrix, and we targeted some outputs like this. Very simple. For 2 focus points, it works well. But when you ask for more difficult, more complex images, it starts, because it's dividing the flux, and you get into the noise floor, and then you are not doing what you want. Here we put random inputs. We compare what we measure in experiments with what the transmission matrix predicts, and you see it's not working. So SNR is already a problem in optics. Well, that's my point. And we will see that AI can do a better job by training surrogate models that do a better job than Tikhonov regularization. Sorry if it got a bit technical in this one. So what is it? Our optical neural network. So there's a laser, sends some light, and there's a micro display here. This is an amplitude modulator. It allows sending an image in amplitude. And the image goes through a 4F system and is sent to an SLM. So this and that, they are conjugated. They are pixel-to-pixel correspondence between the display and the SLM. So this will be where the weights are, and then we are going to read out here on the camera what's the output. So I told you, when you see a physical neural network paper, you have to first ask yourself, where is the input? Okay, let's do that. Let's go through this. The input is here. Let's call it X. It's an amplitude modulator. It will be an image of the MNIST database, which we augment a little bit by, this is a 6, we rotate always in the same sequence to put more flux and more data in the system. This is a bit of a trick. Then the weights, where are they? The ones that you can train, they are on the SLM. They are physical weights only that you can train. And it's a bunch of phases, 2 million of them. And then the output is on the camera, and it's something like this. So you get some field that you measure, an amplitude only measurement, and you define some boxes on this image where you would like that if I have a 6 there, we focus the light on the 6. So here it doesn't work, okay? And then you're going to do multiple iteration, multiple layers of this. So I'm going to retake that image, put it as an input, change my weights until I get focusing on the 6. That's basically what we do in this experiment. So where's the nonlinearity? We have readout nonlinearity here. And sometimes we use also structural nonlinearity. So we repeat the input data on the weekly, a little bit of it. This is a small coefficient on the phase mask. So as I said, the second step is we take that output that was not working, we send it back, we have to update the weights, and then we hope that at the end we focus the light on the 6. And this should work for all numbers we start with.
So when you say you re-inject, is this the inference consisting of multiple cycles or only the training? What are you describing there?
Training. And the inference.
So the inference
to
also
remember-
consists of re-injecting this lower
Yes.
output controller.
Yes. And you need to remember what was the word for each layer. We call this a layer, an effective layer. So the question is how you train this. Was there another?
I still don't understand. How come you want to take the output and inject it back in? It seems weird that the like classification output be injected back in. What's the logic for this? Is it like 2 layers in a sense?
So, yes, exactly. So you would like ideally to do it all in just one shot, but you can't. It's a little bit too complex, so you are going to get to it little by little with layers. So how do you train? So we have this review paper where we describe a lot of different physical neural network training techniques. We're going to use one of the simplest ones, which is physics-aware backpropagation. So what does it mean? It means that you use your physical system to go from the input to the output, but you have a differentiable model on which you can use backpropagation. It's basically a surrogate model. I will show you the topology. It's a neural network, a digital one, that you use just to estimate the gradients. So this is how it looks like. It's a UNet. I don't have to go in details because it doesn't really matter. What matters is that it works well. So for example, there is the input and there is the phase. That's the input of the surrogate. And it needs to predict the output of the camera. So this is the real ground truth output of the experiment. This is what the surrogate predicts. And we train on figures, but also on random stuff, both on the phase and on the input. Okay. What else can we do with our network? We can do multi-channel diffractive optical neural network. So we divide our input image into some channels, and we want to process the data as a batch. So we have many channels, channel 1, 2, 3, 4, we have 16 of them here. And each of them will be independently classifying a given number. Okay, it's tough because you have to align them really well. And for those doing optics, you know it's hard. So we have automatic alignment procedure that we performed. So here we send we are supposed to have the same speckle on all channels, but before we do this calibration we don't. And if we average all these speckles, we just see a blur. And after calibration, you can retrieve some sort of coherent sum. So you can see that they are almost uniform. There is less than 1 pixel mismatch misalignment between each channel. So let's skip this noise thing. So when you do multi-channel, you need to slightly update the surrogate. You don't want to train 16 surrogates. You need to be careful because each of these channels is still a little bit different. You cannot use the same surrogate for everybody. That's what we found out. So you need to sort of embed in which channel you are. And let's show the results and I will be done. This is for single channel. So here we just have one channel and this is supposed to go like this. So this is a 5, 0, 1, 2, 3, 4, 5. So we should focus the light in the 5th square. And for 1, 0, 1. That's where we have the most light. And we have 92% for 3 layers without structural nonlinearity here. And when we do the 16 channel case, we managed to have also a good result, more than around 83 to 85, I don't remember exactly, percent accuracy. And this is the result. So this shows you only 2 of the channels, the first 2. And you see that when we have 0, 1, 2, we will focus into the right squares. And sometimes it doesn't work. You can find 1 or 2 cases where it doesn't work well. This one, for example, is a bit spread out. That's why the accuracy is 80 something. So just to conclude, we calculated the accuracy for all the channels. We have 16 of them. Some of them are as good as the single channel case we had before. Some of them are a bit lower, but on average we are at 86 or 56%. So to stop here, we worked on a diffractive optical neural network where we send some image and the light is scattered and it will be focused into some locations on the camera. In the single channel case, we have 90%-ish accuracy on MNIST, and we used physics-aware backpropagation. Means we have a digital twin and we do the backpropagation on the digital twin, then we go back to the experiment and we do this to updated weights. And we are working towards multi-channel operation. You could process different things on different channels. You don't have to do only MNIST. You could do text plus image. You could do many interesting things. And we are working also on backpropagation free training methods on this system. So far, we tried one thing that is not really satisfactory. So we're around 65%, which is not yet. But you have a lot of things you can change to make it better. So let's see if we can make it. All right. Thank you very much.